Question 39. This is on meters, and you can find out more information on meters in learning task 9 of module A1 or in module C4. It talks a lot about meters as well. This question in particular is about the D'Arsonval movement in a meter. It being rated for 10 milliamps. So I believe the D'Arsonval movement is how the needle in an analog meter moves. It uses some delicate equipment, so it's only actually rated to handle 10 milliamps, which is a very small amount of current. But as you know, there are certain situations where you might use a meter to measure very high amperage, but we need to make sure that that current doesn't travel through the sensitive equipment that makes that meter actually physically move. So in electrical and electronics, you use something called a shunt. And the shunt is like a detour for a lot of current to take. That'll distract it, in a sense, from that delicate and sensitive equipment. So you could represent the D'Arsonval movement in a meter. It's going to be essentially a load, a resistor. So we could draw something like a small delicate resistor here. This area here is what is going to make the needle in a meter actually move. So that is only rated for 10 milliamps. Very small amount of current. And it has a resistance of 150 ohms. But the meter itself is on a 50 amp maximum setting. So 50 amps should be available at this meter. 50 amps is going to be traveling through here. So what we do is we put a shunt in parallel, a shunt resistor. And this is going to distract the majority of current and have it flow down here rather than through here. So we have 10 milliamps here, and that resistor is sized to create that 10 milliamps. So we need to figure out what the, sorry, that was my phone. We need to figure out what the resistant value of this shunt is going to be. Okay, well, the first thing we can do here is we can determine what the current is going to be going through the shunt. And so Kirchhoff's law, he states that the current going into a circuit must equal the current going out. So at this point here, we must have 50 amps. And if we have 10 milliamps here going through the sensitive equipment, then the remainder, the difference, must be going through the shunt. And that's going to be 49.99 amps. So the vast majority needs to be going through the shunt. Okay, the other thing we can conclude, so again, a lot of these equations boil down to knowing Kirchhoff's current law, Kirchhoff's voltage law, and Ohm's law and Watt's law. If you can remember those, you're going to be able to solve the majority of electrical questions in level 1. So if we have 150 ohms and 10 milliamps there, we can figure out the voltage. If you know two values, then you can figure out the third value. So voltage is going to be equal to I times R, which is 150 times 0.01, which is our 10 milliamps. 10 milliamps. And that's going to give us a voltage of 1.5 volts. So if we have 1.5 volts up here, we must have 1.5 volts at our shunt, because they're in parallel, right? So again, if we're measuring from this point to this point, with the voltmeter, we would measure 1.5 volts, but as you can see, that's the exact same point. That's across our shunt. When you have two resistors in parallel, they're going to share the exact same voltage. Okay, so we know that there's 1.5 volts going through the shunt. Again, we're going to use Ohm's law this time to find resistance. So if we transpose our formula, all we got to do is we'll bring I down to the other side of the equation and now to the bottom. That's going to isolate our R. So R is equal to voltage over current. So R is equal to 1.5 divided by 49.99. And that's going to give us a resistance of 3 milliohms. Or 0.03, oops, sorry, 0.003 ohms. Oh, apologize. Let me do my calculation again. So 1.5 divided by 49.99 is going to give me, I better take out my calculator again, divided by 49.99 is going to be 0.03 ohms, which is equal to 30 milliohms. So the answer is going to be C. That's the resistance I need at my shunt. And you can see that too, right? 30 million, oh man, sorry about that. 30 milliohms is a lot less. And so there's going to be much more current that's going to want to flow through your shunt rather than through the sensitive equipment up here, which is 150 ohms of resistance. So remember, current wants to take the least path of resistance. So much more is going to go through the shunt, and that is going to save the sensitive equipment and keep it and maintain it at 10 milliamps.